This is another example of determining the certain orbits of a permutation sigma here. We are still on S8 because we have 8 elements here. And what we just need to do is to look for the sets containing the related elements pertaining on this idea that for A and B, element for our A, or in this case S8, we'll let A be related to B if and only if B is a result when we operate our permutation with a certain mapping from A for some n element of the set of integers. So if we could look for the related elements by a certain idea of the mapping, so and contain them into one set, so we can have the orbits. So one thing we also need to remember if we talk about orbits is that we would like to make sure that we do not share elements to any other orbit. So in short, the orbit should be disjoint. So let's start with the mapping from 1. So we have here 1 is mapped to 2. So you have here 1 and 2. In this case, 1 is related to 2. So if we have here a certain set, we have 1, we are not really sure that 2 is part in the orbit of 1. Okay? If we are going to continue this, let's say squared, this is just equal to saying the mapping of 2. Because if we have here this one, of course, you have 1, 2, 3, 4, 5, 6, 7, 8. We are multiplying sigma to itself. 2, 3, 5, 1, 4, 6, 8, 7. Just an illustration, pardon. I just would like to illustrate this. So 2, 3, 5, 1, 4, 6, 8, and 7. Of course, from right to left, as mentioned, when we multiply permutations, so 1 is mapped to 2, but for this here, you will now start with 2, right? So meaning, if we're going to have these expressions and still pertaining on the mapping of 1, we will just be saying we map the mapping of 2. In this case here, 2 is mapped to 3. So we can add the 3 here now safely. Then if we're going to increase it, so you have the square of 3, no longer square. Okay. So you have here 3. So 3 is now mapped to 5. So you have 1, 2, 3, and 5. Okay? And then we continue with this. So you have to the fourth, n is now equal to 4. So you have here 5. So 5 is mapped to 4. So we still have 4 here. If we're going to continue, okay, that's the fifth, the 5, n is now equal to 5. So it's just equal to the mapping of 4. 4 returns to 1. So we ended the cycle, or not necessarily the word cycle because there are other meaning for cycle, but we ended the pattern. So if we're going to continue, we'll just return here. So with this would be our first orbit. We have 5 elements, 1, 2, 3, 5, and 4. Or you can rearrange it 1, 2, 3, 4, 5. But just a practice for this, because if I'm not saying or declaring it right now, but if we're going to continue looking for the term cycle, the arrangement is very important. So let's just have it like this. Or again, since it's a set, it's acceptable to rearrange them. And as you can see, 1, 2, 3, 4, and 5 is already here. So these elements should not be present in other orbits. Let's continue to the orbit of 6. Okay. 6. So 6. That's it. 6 is 6. Okay. We only have one element for that. So we have here on 7. 7 is mapped to 8. So if we're going to have the second mapping, so that's 8 returns to 7. So our next orbit is 7 and 8. So you have here and here. As you can see, no element is shared between this or among these 3 sets. And as you can see as well, if we're going to combine them, 1, 2, 3, 4, 5, you have here 6, 7, and 8. They are all disjoint at the same time. Their combination is S8, your original set. Okay, so this is how we do determining the orbits of a permutation sigma. Thank you very much for watching.